Okay, so let's continue with discriminants. I said last time, as I said, that we would look at how to make a basis of algebraic integers into an integral basis. So for this, we have this. I'm going to start with this very useful lemma. So this is lemma 2.2.7, which says the following. So as usual, K be a number field. And B some set of elements, say B1 to Bn, a basis for K over Q, consisting of algebraic integers. So we don't know if this is an integral basis, but we at least have a basis and it has all algebraic integers in it. So this is maybe a candidate for what I want to do. So now what the lemma says is, if B is not an integral basis, so let me remind you, an integral basis means that it generates the ring of integers. Just because you have a basis which consists of rings of integers, consists of algebraic integers, doesn't mean it generates the ring of algebraic integers. This is a slightly annoying thing about these things. So if you had a basis which was not an integral basis, then there exists an algebraic integer of the form, say, I'm going to call it alpha. I'm just going to write x1, b1, xn, bn over p, where p is a prime number, and these coefficients, these xi, are all between 0 and p minus 1. And not all of the xi are 0. So they're not all 0. So first part, moreover, so if you had a basis which turned out to not be an integral basis, then you'd have such an algebraic integer in your field. And moreover, if, say, xi is different from 0, so we know that at least some of them are non-zero, so at least one of them is non-zero, and we let, say, b primed be what you get by replacing, so you take the bi in here, and you replace it with this alpha, then you get a new basis, and then we're going to relate the discriminants. So if we let xi, if say xi is different from 0, we let bi be the basis we get by replacing bi with alpha, then here's how the two discriminants are related. So the discriminant of your new basis is xi squared over p squared times the discriminant of your old basis. In particular, p squared has to divide the discriminant of b. So these discriminants, as we saw last time, if I take a basis of consisting of algebraic integers, this discriminant is an integer. So these two things are integers, and here I have a p squared, so p squared has to divide this thing. Okay, so let's prove this. So proof. So let's assume that, as I said, if b is not an integral basis, so if b is not an integral basis, if it's not an integral basis, then we can find some element of the following form. Then we can find say some phi, and I'm going to write as phi1 b1 plus phi m bn, with the yi not all in z. So for this to be had it been an integral basis, then one of these coefficients, if you had an integral basis, then every algebraic integer can be written in terms of that basis, and the coefficients will all be integers. But we're assuming that we don't have an integral basis. So one of the, because b isn't an integral basis, one of these things we have to find, we should be able to find one element where one of the yi's aren't all integer. Great. So we've done that. So now let's consider the least common multiple of all of the denominators of these yi's. So all these yi's are like rational numbers. Let's consider all their denominators. So I'm going to let n be the the least common multiple, the LCM of the denominators of the yi, and I'm going to let p be some prime number dividing n. Let p be a prime dividing n. So n isn't 1 because we're assuming that one of the yi's is not an integer. So one of them, there exists a denominator. So now consider, now let's do this, consider the following multiple. Now consider n over p. So I take this number, n over p, and I multiply this by my original 5. Then all the coefficients in this new number that I've created here. So I've taken 5, I've just multiplied through by this number. Then all the coefficients of the bi are in 1 over pz. So I just mean that the denominator is either 1 or p, or some power of p, i.e. the denominator is either 1 or a power of p. Well, I'm guessing, yeah, power of p, let's say. And we know that at least one of them has denominator p. So, and at least one of the coefficients has denominator p, because I've taken the, these yi's weren't all integers, so there wasn't a denominator. So by relabeling, so just change the names. So by relabeling, we have, say, I should maybe call this phi primes, but well, I'm just going to call it phi again. We can assume that we have something like this, an element like this, phi n bn, with these gamma is now in 1 over p z. So now let's look at the following number. So I'll call it psi, which is what you get if you take change the coefficients for their floors. So this is like the smallest integer, the largest integer smaller than y1, say, because this is a rational number. So we consider this expression. This is a psi. This is just the integer part. That's the floor function just gives the integer part. Then both phi and psi are algebraic integers. Why is this? Well, phi originally was an algebraic integer, we took up here. And psi, it's a linear combination, and these bi's are all algebraic integers by our assumption of the theorem. So we have a basis bi's consisting of algebraic integers. So these two things are algebraic integers, and therefore, because you have a ring of algebraic integers, their difference is also an algebraic integer. Therefore, so is let's get this right, theta, which I'm going to call phi minus psi. And if you consider what the difference of these two things are, when you subtract one from the other, and we note that by construction, phi has coefficients. By coefficients, I mean the coefficients of the bi, and the coefficients are of the form say xi over p, with xi in 0, p minus 1, and they are not all 0. Why? Because we're still assuming that one of these yi's isn't an integer. So here you have some of these yi's are going to be a rational number, and here are just integers, so they can't coincide. So what I'm, this xi minus p, this is just what I get from yi minus the floor of yi. By how I've relabeled things, this is what things look like. Here the xi's are actual integers. So this gives setting alpha equal to theta, we get the first part. All right. Remember that for the first part, what we wanted was wanted to show that there existed an algebraic integer of this form, alpha, where these xi's were between 0 and p minus 1, they weren't all 0. And we've done this. So now let's consider what happens if I swap one of the basis elements with this new alpha and how this changes the discriminant. So assume now, say xi is different from 0. I know not all of them are 0, so one of them is 0. And replace, it doesn't matter which one, and replace, say, bi with alpha. We then get a new basis. B primed, again consisting of algebraic integers, because alpha is an algebraic integer by construction. Next, let's think of what the change of basis matrix is here. Note that the change of basis matrix, so this is just a simple computation, change of a basis matrix from B to B prime. If you work it out, most of the time we've not changed anything. You get 0, all of these are the same. In the ith column, you get, say, x1 over p, x2 over p, xn over p, and then you get more zeros, in the 1 and 0, and then at the end you get 0, 0, all the way zeros and to a 1 at the end. So in the ith, if you write your new basis in terms of the old one, you'll see that this is, all of the columns are the same, apart from the ith one where all of these coefficients, these xi's over p, show up. And this matrix has determinant xi over p. I'll let you figure that out. So note, this has determinant xi over p, and therefore one of our previous propositions, by proposition 2.2.4, we see that. So we had a proposition before which told us how discriminants of two different bases were related, and what was coming up was a factor of the determinant squared of your change of basis matrix. And so this is what's happening here. So we see that the discriminant of b primed is the determinant squared, so it's this thing times your previous determinant. But as I said before, but since these two numbers are integers, it follows that p squared has to divide the discriminant of b. So and this is the end of the proof. What's the takeaway from this result? Which is, well, say you were trying to find an integral basis. The first step that you do is you take a basis and you make it of algebraic integers. That's actually not so hard to do, but it might not be an integral basis. So you look at this lemma, and you construct an element which isn't in this some element alpha, and you change your basis, and now you've constructed a new basis with a discriminant strictly smaller than your previous one. And what's going to happen is that eventually this will terminate. You just make smaller bases with smaller and smaller discriminants, and then at some point the process will stop, and you will end up, this is what we're going to prove, you'll end up with an integral basis. And the other thing to note is that if you had an integral basis and there's a square showing up in the discriminant, then this might not be an integral basis. I say might not, but it could be the case, if I remember correctly. But anyway, here's a corollary of this. So I'll just what I was saying, 2.2.8. is there exists an integral basis. So there exists a finite. I don't think the word finite should need because we're working with number fields. Finite integral basis. In K, what's the proof of this? So yeah, the fact that it's finite follows from this degree, the fact that you have a number field, so this degree is less than infinity. So that B be a basis consisting of algebraic integers. So you might think, how do I know that one of a basis of consisting of algebraic integers exists? Well, you can always take a basis, and we showed ages ago that if I give you an algebraic number, I can always multiply it by some integer to make it an algebraic integer. And if you think about what this will do to your basis, this won't affect the fact that you're basis over Q. So you can take any basis you want. It might have algebraic numbers, so it might not be algebraic integers. But then you can always just multiply through all of your basis elements by some integer, make them all algebraic integers, and this is going to still be a basis for your space, for your field, but it might not be a basis for your ring of integers. So let B be a basis consisting of algebraic integers. Now, by repeatedly applying the previous lemma, so lemma, what was it, 2.2.7, we obtain a new basis, say, a new basis B prime, such that the absolute value of the size of this, so the discriminants could be negative, but in absolute value that this number is as small as possible. Now on claim this must now be an integral basis. Otherwise, yeah, if you use this lemma again, we would get a new basis, another new basis, a new basis, say B double primed, such that the absolute value of the discriminant was smaller than the one that you started with. Well, the one with the B primed, which can't happen. Can't happen. Since we assumed that we had done this all the way down until the discriminant was as small as possible. So that this contradicts our choice of B primed. So an integral basis always exists, and this lemma is somehow telling you how to do this. Here's a fun little corollary. So, corollary 2.2.9. B is a basis consisting of algebraic integers, and the discriminant of B is a square free. So remember, this square free means that if you factorize this, there is no prime that shows up more than once. So there's no square factor showing up, right? So 12 is not square free because you have 2 showing up. You have it's 4 times 3, and the 4 is 2 squared. But if you had a basis consisting of algebraic integers and the discriminant was square free, then B is an integral basis. Why is that the case? Well, let's think of applying this lemma again. It tells us that we can always find a small, that if you weren't an integral basis, you apply the lemma and you get a new one which is smaller, and the discriminant somehow has been divided by p squared. But the number that I started with isn't divisible by any square, so I can't have I can't have done this. So yeah, proof. This is immediate from lemma 2.2.7. Right, so the new base. Yeah, I can't divide my old discriminant by p squared because there's no p squared that divides it. Then let me do a warning here, which I've written in the notes. The converse isn't true. Note that the converse is not true. Example, if you take the Gaussian integers q square root minus 1, then if you take this basis 1 and the square root of minus 1, maybe call that I, this is an integral basis. But the discriminant of b is 4, or minus 4 actually. Great, so here's once we have all of this, as I've said already in words, we somehow get an algorithm for finding an integral basis. So using all this, get an algorithm for computing an integral basis. So what are the steps? 1, first pick a basis. B, consisting of algebraic integers, and calculate the discriminant. So you do this. Next, for each prime p such that p squared divides this discriminant, use this lemma. So use lemma 2.2.7 to find the new basis. B prime such that B prime has smaller discriminant. And now, third is just repeat step 1 with your new basis. Step 1 with the, you don't have to repeat the whole step 1, but with the new basis. So you'll know it's a basis, so you don't have to pick a new basis. So you have your new thing, you compute the discriminant of this new one. It's going to be smaller, so there'll be less primes showing up. And then now there's a smaller list of primes such that their square divides the new discriminant, and do this. And every time you do this, you're going to somehow take out a factor of p squared off the discriminant, and then eventually it's going to complete. So here's an example. So let k be q square root 5, and let's take b to be what you maybe want to assume is a basis, 1 and root 5. Then we have, if you compute the discriminant of this, discriminant of b, you'll find is 2 squared times 5. So not square free. Not square free, so there's something we need to do, something we need to check at least. So if you apply now at 2.2.7, if you work through, you'll find you get a new basis. Say b primed, it's going to be 1 plus root 5 over 2, which has discriminant of this thing is now 5, and now by the corollary we had it, I now have a discriminant which is square free, so this has to be integral basis, which has this. Therefore, this is let's say which is square free. Therefore, this is an integral basis. therefore, oh, actually, this, I didn't speak for precise. Therefore, B primed is an integral basis. Great. 4, okay. Great. So we somehow have an algorithm now to compute integral bases. I'll tell you some more tricks later on for doing this more efficiently in some cases, but at least we have a start. And here's a proposition which tells us something interesting about the discriminants of these integral bases, and which is that they don't change. Which means that the discriminant of an integral basis is an invariant of our field. So it's a number that we can attach to our field, which can help us study it. So if I let B and B primed be two integral bases for a number field K, then their discriminants are the same. Great, so once we have an integral basis, then our discriminant is somehow well defined. So proof, this is quite simple. We somehow consider what the change of basis matrix would be, and then this change of basis matrix, we have to determine determinant 1 or minus 1, doesn't matter. When you square it, you just get the same thing. So in this case, the change of basis matrix from B to B primed is an invertible matrix. Yeah. Matrix with integer coefficients. Maybe I should explain this. So the change of basis matrix, the entries of it are going to depend on what you're changing basis from. Because we're changing between two integral bases, the change of basis matrix is also going to have just integers in it. So this matrix is going to just have integers in it. But because the change of basis matrix are always invertible. So we have a matrix with integer entries, which is invertible. And if you think about this a little bit, this means that the determinant has to be plus or minus 1. Or this is some fact from linear algebra. So its determinant is a plus or minus 1. So now using proposition 2.2.4, we see that the discriminant of B has to be equal to the discriminant of, well, you have plus or minus 1 squared times the discriminant of your other one, which is just either of those things. So we're done. Great. So with this, let me just finish this bit with a definition. So if I let, what number is it? This definition 2.2.14. Let K be a number field. And B an integral basis. Then we define the discriminant of K as the discriminant of our integral basis. By the previous thing, this is well defined. So by proposition 2.2.13, this is well defined, so it makes sense. It doesn't depend on our choice of integral basis. I'm sometimes going to give this an easier name, so we will usually denote this. We will this by just the discriminant of the ring of integers. So this is what I usually denote by a discriminant of your number field. Great. So I'll stop here, and then the next time what we're going to look at is formula for calculating discriminants, which will be quite useful.